Good afternoon. This is Dr. Pradhan here. Welcome to NPTEL project on econometric modeling. So, today we will continue the time series modeling. In the last couple of lectures, we have discussed the entire framework of time series modeling. Means we have discussed how it is different to cross sectional modeling and panel data modeling. And under time series modeling, we have discussed various issues, various types of time series modeling. In that too, we have discussed the volatility aspects of econometric modeling. Okay, basically time series modeling is divided into two parts: univariate time series modeling and multivariate time series modeling. And again, under multivariate time series modeling, there are two different types of models we usually handle. One is called as a distributive lag model, another is called as a autoregressive lag models. Okay. So, there is also mechanism how to transfer the distributive lag model to autoregressive lag models. So, because most of the cases and most of the situation in the higher levels, we will handle directly with autoregressive models. So, the difference between these two is that in the case of distributive lag models, it is the endogenous variable as a function of exogenous variables and the error terms. Means exogenous variables with respect to its current time periods and its lag. Okay. Similarly, in the case of autoregressive lag models, so endogenous variable as a function of exogenous variable and its lag and endogenous lag and error term. So, like this. So, in the case of time series modeling basically divided into two parts: univariate time series modeling, then multivariate time series modeling. Okay. In the case of multivariate time series modeling, so we have discussed distributive lag models and autoregressive lag models. Okay. So, here the framework is like this: y t equal to alpha plus beta x t plus summation beta I x t minus I equal to 1 to n. Okay. So, this is better we call it beta 0, then this sides y t equal to alpha plus beta x t plus gamma y t minus 1. For simplicity, we are just putting small simple models like this, or this is obviously u t, or if you like so simples, then it is better to put y t equal to alpha plus beta 0 x t plus beta 1 x t minus 1 plus u t. Okay. So, this is u t minus 1, this is u t. So, this more or less same. So, there is a mechanism how you have to transfer in this particular format. So, that means these two are more or less same. So, this is how what we have already discussed in the last couple of lectures. So, the basic framework is means first I will once again highlight the various forms of time series modeling. Then we will discuss various issues and problems related to time series modeling, and that too here we have to discuss two aspects of time series modeling, that too unit root and co-integrations. So, unit root is one of the typical problems we have to understand or you have to explore in the case of time series modeling, and on the other side co-integration, it is a multivariate framework. So, that means for co-integration techniques you must have at least two variables in the systems, while in the case of unit root there is no such conditions. So, you can start with one variable at a time. Okay. So, means in the case of unit root, the objective is to know the particular features of a particular variables. Okay. So, we will discuss details once you will enter to this unit root concept. So, first of all, what is the basic, what are the various types of modeling we have to usually handle. So, I will briefly highlight all these things, then we will come down to a unit root test. Okay. So, as I have mentioned, there is means there are two divisions of time series modeling. One is called as a univariate time series modeling, another is called as a multivariate time series modeling. So, in the case of univariate time series modeling, so we will put alpha plus beta x t plus u t. Okay. So, in the case of this is obviously u t. So, then u t y t equal to alpha plus beta x t beta 0 x t, okay, plus summation beta I x t minus I equal to 1 to n plus u t. This is another form of the models. So, then another form of the model is alpha plus beta x t plus gamma y t minus 1 plus ut. Then similarly, I can write like this: alpha plus summation beta I x t minus I equal to 0 to n plus summation gamma I y t minus or gamma j y t minus j equal to 1 to n plus b t. Okay, this is another form of the model. Then we can also write alpha plus beta 1 x t beta x t plus beta 2 x t squares, okay, x t squares plus beta 3 x t minus 1 plus beta 4 x t minus beta 4 x t minus 1 whole squares. Okay, it will continue plus b t. This is another form of the models. So, there is another form of models called as a y t equal to alpha plus beta 0 x t plus beta 1 x t minus 1 plus continue plus b t, and another form of the model is alpha plus summation beta x t minus I beta I equal to 1 to n plus summation gamma j u t minus j equal to 1 to n plus epsilon t. Okay. So, these are the various forms of the time series modeling. So, what means we have to explore in various aspects. In the last class, we have discussed this particular model, particularly this type of models, that to we have discussed autoregressives, moving average, ARMA autoregressive moving average, then ARIMA autoregressive integrated moving average, then we have discussed arch models, and also we have discussed Gauch models, autoregressive conditional heteroscedasticity and autoregressive generalized autoregressive conditional heteroscedasticity. Okay. So, these are the components we have discussed in the last couple of lectures. So, this is univariate time series modeling, and these are all called as a multivariate time series modeling. Okay. So, that too this is purely distributive log models. So, this is autoregressive log models, this is in fact autoregressive log models. So, this is polynomial log models, polynomial distributive log models, then this is infinite distributive log models, and this is ARMA models. Okay. This is ARMA models. So, these are the various typical features of time series modeling. So, that means time series has a lots of issues and lots of concepts. So, so many concepts in front of you. So, we have to handle one particular problems. Okay. So, means at a particular point of time you may go through any particular models. Okay. So, the as usual the basic framework of this particular modeling is that, so you have to fit a proper proper functional form of the models and proper estimated models with respect to all these specifications, means all these tests like specification test, goodness fit test or DG test. So, in the means that means we have to every time we have to go through the estimated parameters and the overall fitness of the models, that to ANOVA statistic like analysis of means like R square, adjusted R square. So, that is mostly on analysis of variance. Okay. So, in the other sides, so we may have diagnostic test like root mean square error, root square errors, then mean absolute deviations, mean absolute percentage errors. So, these are the things we have to incorporate at a time in the case of time series modeling. So, these means at a particular point of time we are very much concerned about the estimation of a particular models. Okay. So, before estimation of a particular model, so we have to be very careful about so many things. The way when we talk about the cross sectional modeling and penal data modeling, that to simultaneous or structural equation modeling, whatever may be the issues. So, every time, so we start with the application of OLS, then ultimately OLS has a certain assumption, and subsequently once you have the estimated model. So, then we have to come back to again assumptions, and assumptions has to be checked properly. If it is okay, then that model can be considered as the best models and can be used for forecasting your policy use, provided it has gone through all these specification test, reliability test or something. Okay. So, that means altogether, so we need to have a good models which can be used for forecasting and policy use. So, now as a result, so we are going through various shapes and various structures, and one of the structure here is the time series structures, that to various forms of the models. In fact, in the cross sectional modeling, panel data modeling, we have no such speciality. That is how the time series is all about to, means it has a lots of uniqueness, that if there are various forms of the econometric modeling we will generate or we will create in comparison with cross sectional modeling and panel data modeling. So, since it is lag involvement, so we will create several forms of the model, and it is very interesting, very more complex in fact, and also very justified so far as a forecasting and policy use is concerned. But before we going to estimate all these models, any one of the models, and for keeping in mind that you need estimated parameters and overall fitness of the models and all these dynamic elements. So, in every case, so you must start with your OLS techniques, but before that you have lots of standard assumptions, and let us assume that all these standard assumptions are also here. But here one of the more interesting point is that the stationarity issue. Okay. So, I will come down to that stationarity issue. The stationarity issue is more or less you can say unity root problem. So, before you go to particular unity root problems, so I typically highlight few features of the time series modeling. That means, we like to highlight what is the problem aspects of time series modeling. Means in other words, we are very much concerned what are the aspects we have to know or we have to explore in a better way or in a broad way, so that the time series speciality can be recognized properly. In fact, it is somewhat different from the cross sectional modeling. In the case of cross sectional modeling, the shape and structure is more or less very simple, but in the case of time series modeling, the shape and structures are somewhat very complex. Okay. So, the various types of model will give you an indication that there are the problems. Time series modeling is a complex problems, and it has lots of additional features which are not there in the case of cross sectional modelings. Okay. So, we have to be very serious. Okay. So, that means first of all, what are the problems associated with this time series modeling. So, you at a time you can follow any particular models. Okay. Ultimately, your main aim is how to get the estimated parameters, and as a result, once you means estimated models, then that is with respect to estimated parameters and other detailed statistics, so that we will come to a position to check whether this model is more reliable, more accurate, more appropriate, so that we can use for forecasting. Okay. But there are certain steps we have to follow before you go to estimating this model, means model selection, or you can say any time series modeling. So, you see here. So, what are the problem basically we will see. So, as we have mentioned previously, there is a separate lectures we have gone through, that is called as a identification problem. So, here also same thing. So, there is a identification problems. Okay. Identification problems. So, that means the model may not be perfectly okay, or sometimes you may face problems to handle or to detect whether it is a distributive lag models, or it is a autoregressive lag models, or you can say it may be ARMA models, it may be you can say only autoregressive models. So, so many ways you can find out. It may be you can say distributive lag model, polynomial distributive lag models, or you can say infinite distributive lag models. So, so many ways you have to find out to you can say, or you can enter to any particular problems. But the thing is that, so that particular models must be perfectly okay for you, that is called as a mathematical perfection of the systems. So, if that is not the case, then obviously it is question of imperfect condition of this particular model. So, that is going against this system. So, as a result you must be very particular about this time series system. So, in this particular setup, so identification of problem must be very important. Okay. So, you have to properly identify the particular shape of the model. Second, lag selections. Okay. Lag selection. there is a problem of lag selection, because as I have mentioned, once you start with the time series modeling, even if univariate say or multivariate say, where there are at least two variables in the system, and we have to start integrating with it with their lags. So now you know, when you have one variable, then you can create 100 number of variables also, or you can go for 5 number of variables. But the thing is that it depends upon two things. First thing is you must have enough number of sample observations, and second thing, you cannot choose artificially. So there is a mechanism how to choose the lag length. That means optimum lag length has to be considered. That is why this is very complex process. It is not like that you have to just like cross sectional modeling, you have to just fix the models y equal to alpha plus summation beta I x I. That is all. The problem is just altogether complete, and you have to just get the estimated parameters and other statistics, then you have to go to for the test. But here itself there is additional problems, that is, you know, choice of lag length. Means once choice of lag length is fixed, then you have to get the estimated parameters or other statistic, then you have to go for its reliability checking, or that specification check, or you can say overall fitness of the models, etc., etc. So lag selection is the most important criteria in the case of time series modeling, which we have discussed in the last couple of lectures. Lag selection, basically we use three statistics, you can say Akai information criteria, squash information criteria, and final prediction error, final prediction errors. In fact we have final predictions error. Okay. In fact we have more number of statistics which can choose the optimum lag length, but these three statistics are very standard statistics, and they are frequently used in the time series modeling. So lag selections is very important. So we have to solve this lag selection with the help of the following statistics. Okay. Then third is the estimation problem. Third is the estimation problem. Estimation problem. So estimation problem means, you see here, we usually start with the OLS technique, and if OLS techniques means whatever estimated results you will have with the OLS technique, and that has to be gone through the, you can say that has to be gone through, you can say you can say that that has to gone through overall fitness of the test, etc. So it is very easy to establish that whether this model is perfectly okay or not. Okay, just 1 minute. Okay. So the model estimation, so estimation problem is very important issue here. So we must be very careful whether the model means whether the technique is essentially OLS technique or other techniques like GLS technique or maximum likelihood estimator, etc. So we must be very careful. Okay. So there is as usual estimation problem, and this particular problem is also there in the case of cross sectional modeling. Okay. So estimation problem is there again in the time series modeling. Then most important thing is the stationarity problem. Okay. So then most important thing is the stationarity problems. Okay. So now in the case of stationarity problems, so that is our main agenda in today's discussions. Stationarity issue is that very simple tricks. We will come down again to that particular aspects. It is better I will first highlight, then we will come down to stationarity issue. Fifth, then that is the called as a causality issue. Causality issue. Okay, before that there may be another tricks called as a co-integrations. Okay, co-integrations. That means this is purely multivariate framework, and then causality is also multivariate framework. So multivariate I am saying with respect to 1:2. So if it is one variable in the system, and if there are two variables in the system, so one variable with its lag is not we are considering here multivariate. So multivariate means two particular independent variables, then we have to play the game with their lag involvement. Okay. So then causality issue. Then finally of course there is a diagnostic test, then you know applications, and then finally forecastings. Okay. Then finally forecastings. Okay. So these are the things means this is as usual standard process of any econometric modeling. but here means here in the time series framework. So, the major things are log selections, stationarity problem, co-integration and causality. So, that means, so we have the problem of log selections, okay. Then second is the stationarity problem, then the third is co-integration problem, okay. Then fourth is causality problem, okay. So, now in the next couple of lectures we have to highlight only on these particular aspects, okay. So, log selection in fact we have already discussed. So, our main things which are left is stationarity problem, that is unity root concept, co-integration problems and causality problem. So, we start with the first the stationarity issue, okay. So, first of all what is stationarity, okay. So, this stationarity otherwise called as it is a unity root problem, okay. It is called as a unity root problem, okay. So, first of all what is stationary, okay. Stationary means you see there are theoretical meaning and there is also statistical meaning. So, so far as in this particular structure in that in fact this particular term is very valid and very applicable in the case of time series setting only, okay. So, now statistically stationarity means or unity root means first what is unity root? Unity root means it gives a signal to stationarity issue, okay. So, now what is mean by stationarity? In a statistical framework, stationarity means its mean, variance and covariance. Mean must be exactly equal to 0, constant mean, we can say constant mean, constant variance and constant covariance, okay. For instance, we have a timeline like this way, okay. So, let us say 0 to 500. So, 0 to 100, 0 to 200, 0 to 300 like this. So, every time we will check because it is in the broad game actually, okay. So, we are collecting few samples and we are testing all these things, and of course, the process of selection should be random in nature, so right. So, now so what is the agenda here? So, unit root has a 3 aspects. So, that means it is a mean, let us say there is a variable say x t, okay. So, mean of x t, so that is called as a error of x t must be constant, okay. Let us say mu, okay. So, then variance of x also constant, let us say sigma, and covariance of x t, then x t minus s, let us say it should be also a constant, okay. So, provided here if s equal to 0, then obviously it will come down to variance of x, means what we used to do in the cross sectional setting, we put x I x j, okay, where I equal to j, then it will becomes variance, and when I not equal to j, it will be covariance. So, similarly here x t with x t minus n, this is not simple x, it is obviously all are x t, okay, x t minus s, okay. So, this should be constant, okay. So, that means the time series modeling, it should be a stochastic process, the choice is very much random in nature. So, randomly you will select the things, then you have to find out the mean, variance, means very theoretically, or you can say very at the narrow levels how you have to check the stationarity, etc. Okay. So, then there is a statistical procedures, complicated procedures through which we can easily detect the stationarity issue, etc. Okay. So, now what is mean I x? It is simply like this way, summation y t by t equal to 1 to n divided by, you can say n number of total observation. This is how mean of x t we can derive. Similarly, variance of x t is nothing but y t minus y t bars whole square divided by 1 by n. Okay. So, this is how variance has to be calculated. Similarly, covariance y t minus y t bars into x t minus y t minus 1 into y t minus bar, obviously it should be a constant. So, this is how we have to check the stationarity problem altogether, all right. So, now first of all, what is the basic objective behind this stationarity means unit root. So, now the basic objective of, there are 3 objectives specifically for this unit root problem. First objective is to know the ternarity. Okay, time series all time series variable in a particular system should be ternary. Okay, if it is not ternary, generally particular or not generally, particularly financial time series variables, they are non-ternary in nature. Okay, so that means they have uniform unit root problems in the initial setup, but whether there is a means first you have a variables, then your job is to check whether there is a ternarity or non-ternarity. But most of the cases in the particularly financial time series variables, you will find the variables at the original form is always unit root problems, non-ternary. So then you have to continuously, you can say, difference integrate till you get the variables ternary. Then finally the variables which the difference variable should be used in the final setting. So where the variable is ternary in nature. For instance, there is a variable say x t. Okay, so for instance, there is a variable say x t. So I will call delta x t, I will call delta square x t, I will call delta q x t. So this is how I can proceed. Okay, so this is called as a first difference, this is called as a second difference, third difference. There is a methods like differentiation, there is a difference methods. Okay, so at delta x t means it is nothing but x t minus 1. So okay, delta square x t minus x t means del upon again x t minus 1. Okay, so similarly del 3 means it is del upon again x t minus 1. So this is how we have to be means you have to proceed further till you get ternarity. That means most of the financial time series, the variables may be means variable most probably it is a unit root problem here. So non-ternary. So when we will go for first difference, then obviously the series may be ternary. So once it is ternary, then this variable particularly means the variable, this is called as a transformation rule. Okay, so generally there are two ways you have to use the data in your modeling framework. So either original variable or you can say transferred variable. So there are many ways you can transfer the variables, and one of such important transformation rule particularly for the time series setting is the application of difference equations. Okay, so we are using here difference equation for ternarity checking, and also we have to find out the order of integration where the variable is ternarity, and that order has to be used for, you can say, further estimation process. That is why estimation process is very complicated here in the case of time series study. Until unless you know the order of integration, then obviously it is very difficult to fit a particular models, means particular causality models. All right. So there are three problems. First is know the ternarity, that is, you can say, ternary problems. So ternarity of the time series data. So this is second problem is the order of integrations. Order of integrations means like this one, this is order 1, this is order 2, this is order 3. Okay, so that means the variable means there are various means interpretation is like this. So if the variable is ternary, then you can say that the variable has no unit root problem and it is ternary at the label data. Means in the first instance you are getting the result that there is no unit root problem. So if it is non-ternary, then you have to go to the first difference, then you check again whether it is ternary or non-ternary. If it is ternary, then obviously you have to use that particular orders for further estimation or further investigations. Or if it is again not ternary, then you have to again go for another difference. So this is how this particular term is called as a small d. Okay, d represents order of integrations. Okay, order of integration. Generally, so we means most of the cases you will find the variable is non-ternary at the label data, but when we will go for first difference, so you will get ternary. So most of the first difference level, so that variable is very much useful for the time series setting. Okay, so this is how the structure. And third thing is it will give you signal for co-integrations and causality, because ultimately in the time series settings, so there are three altogether games. So, first is the unit root setup, second is the co-integrations, and third is the causality. So, unit root will give you the testanarity issue. So, until unless you check the testanarity, then the variable cannot be, you cannot proceed further. So, okay, if you proceed further without checking testanarity, that is the wrong way of entering to the time series econometric modeling. So, first entry level is check the testanarity, then you enter to the second level. The second levels, here you have to check the co-integration. That means co-integration means the existence of long run equilibrium relationship. Okay, long run, basically long run relationships. Okay, so we start with the short run analysis, then we will go with the long run analysis. So, short run causality, long run causality, then finally we will end with the direction of causality. Means here time series issues. So, there if there are two variables, say, then either x influence y or y influence x. Okay, so this is how it is called as a, there is a possibility of bidirectional causality, but in the case of cross sectional settings, so we usually go for a one way causality. Okay, except simultaneous structural equation modeling and simultaneous equation modeling. Other case, it is one way causality. That means every times there is one dependent variables and other independent variables, and it is the impact through independent variable to dependent variables. But here the structure is, there is if there are two variables, then there may be chance x causes y and y causes x. Okay, so that is how. So, there are three different issues you will find. So, either they may not cause each other, so they may cause each other at the one way, that means there is one way causality, or it is called as unidirectional causality. That means if x causes y, then y does not cause x, then similarly if y causes x, then x does not cause y. But then if both will cause each other, then it is called as a bidirectional causality. If one cause and another does not exist, then it is called as a unidirectional. If both will not cause each other, then there is a question of no causality. Okay, so these are the complete game of the time series setting, that to this the entire setup here. So, okay. So, now first of all, how to check the testanarity. So, the main aim is here to check the testanarity issue here. Okay. So, now unit root test. So, first we start with checking the testanarity, then you will go for co-integration, then you will go for causality. Okay. So, unit root test has several methods. Okay. So, to check the testanarity, first is called as a decupular test, augmented decupular test, then Phillips Perron test, then called as a KPSS test, then called as a ERSPO test, then it is called as a NP test, NG Perron test, then DFG GLS. Okay. So, that means decupular generalized scarce techniques. Okay. So, there are various techniques. In fact, there are lots of research going on this particular structures to unit root, co-integration and causality. So, our aim is here to check the testanarity of a particular time series variable, means how to check the testanarity of a particular time series variable. So, these are the methods. Any method you will apply, you get the testanarity problems. Okay, you have to detect the testanarity, whether the variable is testanary or non-testanary. That means whether it has a unit root problem or it has not unit root problem. So, some techniques are very complex, some techniques are very simple, and in a particular setup, if you get a result in one technique, then same results you will get from the other technique also, provided there may be some plus minus is there, means something addition, something subtraction, not exactly, but you will get the themes done. Okay. So, so the structure we start with is called as a decupular test. So, what is decupular test? Because basically we will highlight these two test here, because this is very easy to apply and easy to understand, and very quickly you can calculate the estimated value. So, far as a classroom problem is concerned, these two techniques are very useful, very handy, but in these techniques you need to have the use of softwares, otherwise it is very difficult to handle in the classroom. So, let us say start with the decupular. So, what is decupular? Okay. So, it is called as a decupular test. Okay. Decu and Fuller unit root test. Okay. So, what is this decupular? So, it start with the regressing like this way, y t equal to alpha plus rho y t minus 1 plus u t, say. Okay. Minus 1 less than rho less than less than 1. Okay. So, if rho equal to if rho equal to 1, then there is a unit root problem, then there is a unit root problems. Okay. So, if rho mod of rho less than 1, then this variable is stationary, then the variable is a stationarity. Okay. So, this is how the structure is altogether. Okay. So, there are, in fact, there are many versions of the Dickey-Fuller test. Then finally, there is a augmented Dickey-Fuller test. So, that means what you are saying. So, in the very beginning of the time series setting, I clearly highlighted that if you have a variable, then you will create additional variables, because in the time series settings, one of the interesting feature is that the current variables depends upon its past observations. Okay. So, as a result, so there is another variables you have to create. So, yt minus 1, yt minus 2, yt minus 3, like this way. So, this is how you have to proceed. So, that means your current variables will fall off. Okay. So, with this past values. So, now no, so if that is the structure and that structure you are creating, then obviously two major problems you have to face. So, one is by default there will be multi-collinearity problem, and second there will be autocorrelation problem, and both are dangerous for the so far as reliability checking is concerned or overall fitness of the model is concerned. That means, if the problem if the estimated model has autocorrelation problem or multi-collinearity problem, then obviously at the higher level, then obviously that model cannot be used for forecasting and policy use. So, that is why you must be very careful how you have to handle this situation. Obviously, one of the standard trick is that if you use the transfer variable, then obviously most of the problems can be solved. It may not, there may be some plus minus, but most of the problems, for instance, if you apply fast difference, then autocorrelation problem may be solved, and in the same time multi-collinearity problem also solved. So, let me give you signals, because Dickey-Fuller's unit root has a different shapes altogether to check the stationarity issue, because the time series variables has a different shapes and different structures, and with respect to a particular setup. So, you have to use a particular form of the techniques, so that you can able to easily detect the unit root problems or your stationarity issue. Okay. So, this is simple model 1. So, in the model 2, so what you will do, I will put like this way: yt equal to beta 0 plus beta 1 yt minus 1 plus ut. Okay. So, this is dependent variable, this is independent variable, this is error term, this is parameters which like to estimated, and this is most important, because the significance of this will depends means it will give you signal whether there is a unit root or not, and beta 0 is a constant, it is called as a drift. Okay. It is a drift. So, sometimes in the earlier case we have not used any constant. Okay. So, now we are using the constant, and in the model 3, so I will write like this way: yt equal to beta 0 plus beta 1 t plus beta 2 yt minus 1 plus ut. Okay. So, beta 0 is a drift here, then this is a trend, then this is a independent variables. In fact, in between there is the model, I can write a model like this way: yt equal to simply beta 1 t plus beta 2 yt minus 1 plus ut. So, that means, this is when I will write simple models like this, yt equal to rho yt minus 1 plus bt, then this particular model has no drift and no trend. This t stands for, small t stands for trend here. Okay. So, that means beta 1 t. So, that particular weightage will give you the trend factors. Okay. So, drift with the trend, this is without drift and trend, this is drift without trend, this is trend without drift, and this is trend with drift. Okay. So, this particular is called as a trend with drift. Okay. So, that means, so you must have your initial setup may be very stochastic in nature, but you have to come down with a very deterministic trend like this. You see, the structure will be like this way. So, altogether like this. okay, this pictures you will find this particular shapes. So, this particular structure is called as a stochastic stand. Okay, so stochastic strands in between. So, I will give you a structures like this. Okay, I will give you a structures like this way. Okay, this particular structure is called as a deterministic trend. Of course, this is with respect to time and yt. Okay, this is with respect to time and this. So, that means your label variables information in the original labels, or that is what we call label data, then the shape of plotting will be like this way. Okay, so, it will be very much stochastic in nature, but when we will go for transformation, then obviously it will be coming in a deterministic forms. Okay. So, this is the forms you can find out. So, this is the process of integration, means this will give you the process of integrations or integrated process, or you have to you like to know what is the order of integrations to get the deterministic trend. Okay, deterministic trend. So, now we have the structures like this, y t equal to beta 0 plus beta 1 t plus beta 2 y t minus 1 plus u t. Okay. So, these models what we will do. So, I will subtract y t minus 1 both the sides. Okay. So, equal to beta 0 plus beta 1 t plus beta 2 y t minus 1 minus y t minus 1 plus u t. Okay. So, this is I will call it delta y t. Okay. So, this is delta y t. So, beta 0 plus beta 1 t plus beta 2 minus 1 into y t minus 1 plus u t. Okay. So, this particular structure is a decupolar models, it is called as a decupolar's model. So, now I can write delta y t equal to beta 0 plus beta 1 t plus gamma y t minus 1. So, that means here null hypothesis is that gamma should equal to 0 against alternative hypothesis gamma should not equal to 0. So, that means delta should be less than to 0. So, of course, here you have to apply the t statistics to know the significance levels. So, that is nothing but gamma head by standard error of gamma heads. Okay. So, this is how you have to calculate decupolar statistics. So, decupolar statistics has several versions. So, I will give you means if I will summarize, then there are specifically 3 different shapes. Okay. So, first shape is like this. So, it is delta y t is equal to gamma y t minus 1 plus epsilon t. Okay. This is single one forms. Then another is delta y t equal to alpha 0 plus alpha 1 y t minus 1 plus epsilon t. Then delta y t can be alpha 0 plus alpha 1 t plus alpha 2 y t minus 1 plus epsilon t. So, this is without drift and trend, this is with drift, and this is with drift and trend. Okay. So, these are the things of, you can say it is called as a decupolar test statistics. So, decupolar test is generally used to test the stationarity problems, or to check whether the variable is stationary in nature or not. So, now in addition to decupolar test, there is means there is advanced versions. It is actually in the name of two professors, Dickey and Pullers. Okay, Dickey and W. F. Pullers. So, it is with respect to the in response to their names. So, this statistic is called as a ARDF statistics. So, they have given a modified version of statistics. It is otherwise called as a ADP, augmented decupolar test. So, what is this augmented decupolar test? So, this test will be like this. So, it is nothing but delta y t. So, delta y t is equal to alpha y t minus 1 plus extra t delta plus beta 1 or delta y t minus 1 plus beta 2 delta y t minus 2 plus continue sorry, not delta, this is beta actually, then beta p delta y t minus p, okay, plus v t. Okay. So, we start with this particular issues, but ultimately okay, I will come down to the accurate problems because we have not time to come down to the original format. So, here the specific form of the ADF statistic is like this: delta y t equal to beta 1 plus beta 2 t plus delta y t minus 1 okay, plus summations gamma I y t minus I okay, I equal to 1 to n plus u t. Okay. So, this is the typical framework of, you can say, augmented Dickey-Fuller test. Okay. This is typically the framework of augmented Dickey-Fuller test. Okay. It like Dickey-Fuller test, it has 3 different versions. Okay. So, let me highlight the 3 different versions here. So, delta y t equal to delta yes, let us say alpha okay, once again I will be writing. So, delta y t equal to alpha y t minus 1 okay, plus summation gamma I y t minus I equal to 1 to n plus u t. Okay. So, this is model 1, this is in the question of model 1. Then I will write delta y t equal to let us say mu okay, plus alpha y t minus 1 plus summation gamma I y t minus I equal to 1 to n plus u t. Okay. So, this is another forms, it is called as a model 2. Okay. Then I will write like this way: delta y t is equal to mu plus okay, mu 1 plus mu 2 t. Okay. So, then plus plus alpha y t minus 1 plus summation gamma I y t minus I equal to 1 to n plus u t. Okay. This is model 3. So, that means like Dickey-Fuller test. So, we have 3 different sets of models here in the case of augmented Dickey-Fuller test, but only important thing we have added is this particular portions. Okay. So, this is the addition or net addition to the Dickey-Fuller test. So, now because it will give you optimal framework of checking the unit root problems. So, in the first case, in the first models, it is the model with the no trend and no drift. This is with drift no trend, and this is with drift and trend. Okay. So, now in every case our standard objective is not like that way. So, this is the standard, this is not the boundary. Okay. So, now in our objective is to handle this particular framework. Okay, this particular, that means alpha null hypothesis is alpha such that alpha equal to 0, alpha 1 such that alpha alternative hypothesis such that alpha not equal to 0. So, that means in this particular framework your alpha statistics should be statistically significant. If alpha statistic is statistically significant, then we will say that it is stationary in nature. If alpha statistic is not significant, then obviously it is called as a non-stationary problem. So, that means if you further suppose you are not getting a stationarity levels or order of integration at a particular level, in this particular levels you are not getting the stationarity. So, then you will go for second difference. Okay. So, then you will go for third difference. So, like second difference, in the case of second difference, delta square y t will be a summation like this way. It will come in the case of second difference. So, it will come like this way: delta squares y t is equal to alpha 0 plus gamma y t minus 1 plus summation beta I, okay, then delta squares y t minus I okay, t minus I equal to 1 to n plus ut. Okay. So, generally this is different issue, higher versions, but mostly these are the 3 versions we may use, but this is the standard tricks here. So, suppose at this particular levels you are not find this alpha hat is not significant, then again you have to go for first difference, second difference, third difference, etc., etc. So, the moment it will say, suppose it is stationary at the level data, then you can say that the variable indication will be like this way. So, its indication will be say that if it is integrated, then you know say I1. So, if it is integrated at the first difference level, if it is the original level, then it will integrated of 0. So, I integrated of order 1 means you are getting the stationarity at the first difference level. Okay. So, similarly, suppose at the second difference level, so it will be integrated of order 2 like this way. So, if d is the order of integration, then obviously the variable will be stationary at the I upon d. Okay. So, that is how the order of integration can be detected. So, similarly you have to apply in different aspects to check the stationarity issue. So means like you know in the case of KPSS, then Phillips parent test, then you know NG test, etc., NG parent test. So because of lack of time, it is not possible to go through each and every techniques to check the stationarity issue, but most of the generalized and standardized particular variable is the augmented decoupleur test. Okay. So, in fact it is more advanced is sometimes you can check the structural break also in this with the help of this augmented decoupleur test. So, like just in that case you can write like this way: alpha 0 plus alpha 1 d 1 plus alpha 2 d 2 plus gamma y t minus 1 plus summation beta I delta y t minus I equal to 1 to n plus you can say ut. So, d 1 d 2 are the seasonal components, it will give you the breaks whether sometimes you know the issue is why the variable is not stationary. So, there may be some structural break is there. So, if you detect the structural break, then obviously you can get to know the complete picture of stationarity, otherwise it is very difficult to find out the stationarity issue. Anyway, in whatever may be the situations, so one of the standard problem in the time series modeling is unit root test. So, that is to check the stationarity issue, and that is very useful for co-integration and causality test. So, so before you going for co-integration and causality, these are the main objective of a particular time series modeling. So, you must know the stationarity levels, means order of integration where the variable will be stationary. So, there are various techniques available to check the stationarity issue. So, that to unit root problems. So, we start with the decoupleur test, then augmented decoupleur test, you know then Phillips parent test, NG test, etc. So many tests are there, what we have already highlighted, but basically we have briefly discussed the details about decoupleur test and augmented decoupleur test. Decoupleur test is the easiest methods, very simple to understand, very simple to calculate, and its modified version is called as a augmented decoupleur test. So, that is what you know, just you know giving the optimum lag length structures and degrees of freedom adjustment. So, so means that is how augmented decoupleur test is much advanced and you know more interesting, more reliable than the decoupleur test. So, most of the problems, so you can use augmented decoupleur test to check the stationarity issue of a particular time series variables. Okay. So, now so similarly other techniques with you know so many constraints or you know conditions you can apply. Sometimes you know more like you know NG parent test can be applicable in a more advanced way. Sometimes Phillips parent test can be applicable in various ways. So, we are not concerned about all these things, but ultimately our main agenda is to check the stationarity issue. So, whatever techniques you are applying, so ultimately end result is you have to know whether the variables are stationary in nature or not, or means having unit root problems or not unit root problem. If it is unit root problem, then at what levels or at what order of integrations you will get the stationarity, and that order will be use further for co-integration and causality. Okay. So, we will discuss detail about this co-integration causality in the next class. So, for this in the time being, so we can close this class. Thank you very much. Have a nice day.